The ground hasn't moved yet. Down in the city, no warning sirens are wailing. Your phone is completely silent. From the perspective of our highly advanced multi-million-dollar sensor networks, everything is perfectly normal. But look closely at the local wildlife, and a very different picture emerges. Dogs in the neighborhood are whining frantically. Snakes are abandoning their burrows in the dead of winter. Fish are launching themselves out of the water for absolutely no obvious reason. Hours later, a massive earthquake strikes. We tend to write these moments off as strange, unsettling coincidences. Yet this exact sequence, widespread animal panic followed immediately by catastrophic seismic rupture, has been recorded for thousands of years. The immense volume of historical data has reached a point where it is difficult to ignore. Today, many seismologists are looking past the folklore to investigate whether these behaviors constitute a measurable biological warning system. In 373 BC, the Greek historian Diodorus observed something entirely inexplicable. Days before a massive earthquake wiped the city of Halys off the map, rats, snakes, and weasels evacuated the area in enormous numbers. Fast forward to 1975 in China. Authorities noticed snakes waking from hibernation and cattle acting frantic. Based heavily on this erratic animal behavior, officials evacuated the city of Haicheng. The next day, a major earthquake leveled the region. 1 million lives were saved. These are not isolated regional flukes. Highly documented reports of pre-quake animal panic exist across Japan, Italy, Turkey, and the United States. These populations survived because they responded to environmental cues that human biology is entirely unequipped to detect. To figure out exactly what these animals are sensing, we have to look past the surface-level panic and travel deep underground, long before the tectonic plates actually slip. Looking at this cross-section of the Earth's crust, you can see the first invisible force. As the plates grind together under immense pressure, they generate low-frequency sound waves called infrasound. These frequencies fall far below human hearing limits, but animals like elephants, tigers, and birds can detect them. They essentially hear the earthquake building in the rocks below. Then there is the electrical shift. As solid rocks crack under the extreme strain, they release powerful electrical charges, a documented physical process known as piezoelectric activity. Animals that navigate and hunt using electrical fields, like sharks, catfish, and bees, pick up on these sudden underground voltage spikes. Finally, there is a chemical signature. Cracking rocks release trapped radon gas, which slowly filters up through the groundwater and soil. Animals equipped with highly sensitive olfactory systems, particularly dogs and rats, can smell this chemical change rising beneath their feet. These physical signals appear weeks before the ground shakes. A 2020 study based in Peru revealed that wildlife began behaving abnormally up to 23 days before a major earthquake struck. Instruments detected nothing, but the local fauna were already responding to the shifting conditions. What we humans experience as a sudden, violent shock is actually the final stage of a prolonged, multisensory environmental event. The animals are simply reading the room. We can observe these biological receptors triggering in real time. Across the globe, there are consistent reports of domestic dogs exhibiting severe distress, whining, or desperately trying to escape their homes hours before a fault line ruptures. 5 days before the 2009 L'Aquila earthquake in Italy, an entire colony of toads suddenly abandoned their local breeding ponds. Scientists from the Open University later verified this as a genuine stress-induced response to the impending seismic activity. We saw similar survival instincts trigger before the 2004 Indian Ocean tsunami. Hours before the massive wave hit the coast of Sri Lanka, observers watched herds of elephants migrating to higher ground. Most of them reached safety, while the surrounding human population was caught unaware. Even the deep ocean responds. In Japan, the reclusive oarfish is rarely seen alive, yet several of them washed ashore in the days directly preceding the catastrophic 2011 Tohoku earthquake. Whether an amphibian abandoning a pond, an elephant climbing a hill, or a fish fleeing its habitat, these evolutionary adaptations serve as highly specialized geological sensors. The question now is a logistical one. If wildlife naturally senses these events, how do we integrate their biological reactions into a reliable early warning network? Several nations are already attempting it. China maintains formal animal observation programs in high-risk zones. Japan monitors animal behavior alongside traditional hardware. And in Italy, researchers are exploring AI networks to analyze pet behavior data from thousands of households simultaneously. But this system faces a major challenge: false alarms. A dog barking or a bird fleeing a nest can be triggered by weather, illness, or a predator. To make this data actionable, we cannot rely on a single animal. The focus is now on using technology to identify simultaneous, localized behavioral patterns across multiple different species at the exact same time. The persistence of these reports, spanning millennia, is leading modern seismologists to reevaluate what was once dismissed as folklore. While electronic sensors remain our primary tool, researchers are beginning to treat biological data as a serious area of study. From ancient Greek accounts to modern tracked migrations in Italy and Sri Lanka, the patterns are consistent. These aren't just isolated stories, they are consistent data points in a global search for better disaster mitigation. The Earth broadcasts its signals in frequencies we can't hear and chemicals we can't smell. By learning to translate animal reactions into reliable data, we may finally be able to fill the silent gap between the first deep crust shifts and the movement of the surface.